The idea of Big Bang and the origin of the universe has become layperson's knowledge these days. How do cosmologists understand the origin of the universe, and what are the general misconceptions that they avoid?
Let me backtrack for about 60 years. So maybe even 65 years. So 65 years, the word Big Bang was actually a pejorative word. And I have been told that the famous Soviet physicist Zeldovich, when he heard about this idea that the universe was expanding and has been expanding for a long time, he basically said, this cannot be correct, because if it were true, there'd be a cosmic microwave background. So now, 10 years after that, the cosmic microwave background was discovered. And so this is probably the best observational confirmation that the universe has been expanding. And this made cosmologists accept the Big Bang model, which is the idea that the universe has been expanding for a long, long time, and that if you go back in time, the universe becomes hotter and hotter, and the temperature rises without bound if you accept the equations which cosmologists are using. So you go back 13 billion years, and according to the equations which are being used, you find that the temperature goes to infinity. And this is the Big Bang. This is the origin of the universe in a hot fireball. So this is now, if you go back just a little bit less than 13 billion years, you go back a few seconds less, this is now accepted by cosmologists, with a couple of exceptions. So there are also other successes, but I don't want to go into the other successes. But now, when you ask the question, what is the Big Bang? Then, at that point, I think all honest cosmologists will have to say that we don't know. Because infinite temperatures, that means that the theory which we have been using breaks down. So in a certain sense, most of the Big Bang model has been accepted by cosmologists, but not the very beginning. Now, the misconception which the public often has is that the Big Bang is an explosion which happened at one point in space, a huge explosion. But this is not what the Big Bang model is. The Big Bang model is this strange singularity, which says that at some point in the past, space emerges, and space is already finite. It's already big. How big, that depends on which particular cosmologist you listen to. And before that, there was no time and no space, which philosophically raises all kinds of problems.
We live in a universe that is expanding at an accelerated rate, and this acceleration is often attributed to the idea of dark energy. But why is the universe expanding in the first place?
Right, that's a very good question. So when Einstein first started thinking about space and time, he was under the impression that the universe could not be expanding. It had to be eternal and static, like Newton. Okay, so Einstein's ideas were based on the equivalence principle. And so maybe one way to state it is Newton told us that if there's a force that acts from one object on another, there has to be a counterforce. Now, Newtonian gravity has gravity acting on an object that lives in space-time, but that object doesn't back react on the space-time. So Newtonian gravity, in a certain sense, is in violation of the third law, Newton's third law. So Einstein asked the question, how does matter back react on the space-time? And then he developed the model that if you have a concentrated mass, that then this concentrated mass will cause a curvature of space. And one way to explain it figuratively is that space is an elastic sheet. You plunk down a heavy mass on the elastic sheet, and the elastic sheet will be deformed. So Einstein developed equations which describe that very well, and these equations were confirmed by observations, the bending of light, for example. But now if you apply these equations to a distribution of matter which is the same everywhere in space, then the equations tell us that space cannot be static. Space either has to be expanding or contracting, unless you add a highly fine-tuned cosmological constant, this fudge factor. So now this fudge factor is basically, even adding this fudge factor, you don't get a stable static solution, time-independent solution. So Einstein tells us that space cannot be time-independent. If you have matter everywhere, then space has to be either expanding or contracting. And we see it to be expanding. We live in one of the two possible branches.
Time, as we perceive, seems to flow from past to the present to the future. And yet there is no distinction between the past and the future in the laws of physics. Can cosmology help us explain the apparent contradiction in this perceived irreversibility of time?
Let me make an analogy. So the equations of Newtonian mechanics are time translation invariant. So if you go from A to B, for example, you go from India to Ohio, then there are also trajectories that lead you from Ohio back to India. But there are many people who emigrate from India to the United States, and they stay in the United States. So now let's look at what this implies for the equations of space and time. So the equations do not distinguish between going forward in time and backward in time. So we can have a solution in which the universe is expanding. There's also a solution in which the universe is contracting. Okay, so basically there are two possible branches, but now we actually see something special. So if you look at the universe that's expanding, we see structures growing. So according to what we know from cosmology, the universe starts out to be almost space independent. The density is almost uniform in space. That we know from the fact that the microwave background has almost the same temperature in all directions. But today we see lots of galaxies. We see that the universe is very inhomogeneous. So structure has grown. And this implies, in a certain sense, that entropy has grown. And so you can identify the direction of time that we perceive with the direction in which the entropy is increasing. But the question of this, the arrow of time, is a deep question. And there are still people are discussing it very actively. And a colleague of mine, Neil Trorak, he has a model in which the whole universe is time symmetric. And in this picture, there is the universe that we live in which time is appearing to go forwards, and as time goes forward, structures are growing. But in this model of Turok and collaborators, if you take that clock back into the past, there was a cosmological bounce, and you take that clock even further back, then as that clock goes further back in time, then as you go further back in time with that clock, then inhomogeneities grow. And so that clock is then not the clock in terms of which we perceive the entropy to be increasing as the clock goes back, shows earlier times. So this is a deep question that you're asking, but I would say that locally, in the part of the universe that we perceive today, the direction of time is given by the growth of entropy.
In your works, you've actively used the field of string theory in the field of cosmology, leading to what is now known as superstring cosmology. Could you please describe this field?
Well, so the motivation for trying to merge string theory with cosmology comes actually from the breakdown of our standard approach near what is the Big Bang, what I described previously as its infinite temperature. So we know that we need new physics. Infinite temperatures don't make sense. So in string theory, there's good evidence that there should not be, that infinite temperatures are not allowed. So it's been known from the early days of string theory that if you take a box of closed strings and you compress it, then the temperature of that box of strings will initially go up, but then the temperature will level off. And if you make the box extremely small, then the temperature will go down again. So in string theory, there is no temperature singularity. The temperature never becomes infinite in this sense. So if you now apply this to cosmology, you then immediately see the promise that string theory has for cosmology. You can hopefully avoid this bad feature of standard cosmology that the temperature goes to infinity. Okay, so Vafa and I, Kumun Vafa, who's a professor at Harvard, and I started thinking about what kind of cosmology could come out of string theory. So that was the starting point. That was a motivation. And we were influenced heavily by this picture that you have a box of strings and you compress it, you make that box very small, and at some point the temperature starts leveling off. Now, we also discovered that the more entropy you have in a system, and today we have a huge amount of entropy in the universe, so our universe contains a huge amount of entropy. So if you take that universe back into the past using these ideas from string theory, then you will find that there's a very long phase in which the temperature of this gas of strings is almost constant. So that was the starting point of our work. So in our work, we start the evolution of the universe in this phase where the temperature is very close to this maximal temperature. And the universe will live there for a very long time. And eventually, the universe will start expanding. And this happens because of a particular transition in how the gas of strings looks like. But maybe I will wait for a follow-up question on that. So anyway, this was the initial picture. The initial picture is motivated by how a thermal gas of strings is different from a thermal gas of point particles. And that we immediately realize that this will be very important in the early universe. And let me make a provocative comment. My provocative comment is that any approach to early universe cosmology, which does not include this feature that there's a maximal temperature in, if you use strings, and there's no maximal temperature if you just use point particle ideas, that's doomed to failure.
String theory predicts many more dimensions than the observed 4 dimensions of space and time, 3 of space and 1 of time. Can physicists somehow explain how these 4 dimensions that we live in today gained a special status out of all the other predicted dimensions of string theory?
This is a very good question. And this was exactly the question which Kummelwaffe and I addressed in our initial work of 1989. So first of all, let's go back to theories that you had before string theory. These theories can live in any dimension of space. 4, 5, 6, 3. There's nothing that determines the dimension of space. So before string theory, you could ask, why do we live in 4 dimensions of space-time, 3 dimensions of space, 1 dimension of time? And there was absolutely no answer to that. Okay, now comes string theory. And string theory says that the theory is only consistent if you have 9 dimensions of space and 1 dimension of time. Okay, so that's already progress, because we have a distinguished number of dimensions of space. But now you can object and you say, well, this is very nice. String theory makes a prediction, but this is wrong. We don't see 9 dimensions of space. We only see 3 dimensions of space. Okay, so now in our approach, the approach which I just outlined, the approach which we call string gas cosmology, we start with 9 dimensions of space, which are all wrapped by strings. And then we try to make any one of these dimensions of space large. And you cannot do that as long as you have strings wrapping the dimension of space, because the energy of a string that wraps space increases as the size of space becomes larger. And this doesn't work. You can't take the energy from nothing. So in order for any dimension of space to become large, you have to eliminate the strings that wind that spatial dimensions. And that means that strings have to be able to intersect and get rid of basically what we call winding. So you have 2 strings that wind space, let's say almost parallel, they intersect, they form 2 loops, and that allows the dimensional space to expand. Now, this process of strings finding each other and windings going into loops can only happen in maximal 3 spatial dimensions, because in more than 4 large space-time dimensions, strings cannot find each other. So in our model, we actually have a specific mechanism that explains why we have 3 and only 3 large spatial dimensions. And the other 6 are forever wrapped, confined at the string scale, invisible to our experiments.
String theory is considered to be a consistent theory of quantum gravity, but its distinct effects are yet to be observed in experiments. Can cosmology, or the application of string theory in cosmology, can somehow help us confirm these ideas of string theory and gain perspective?
Yes, definitely yes. So string theory, among many people these days, at least in North America, has a bad press. And one of the reasons why it has a bad press is that people say that it is just mathematics, it is unrelated to experiment. And they also say, well, we haven't seen strings at the LHC. And this is true. We haven't seen strings at the LHC, and we will not see strings at the LHC. We will not see strings in accelerated experiments. But in cosmology, we can do that. There are predictions, specific predictions that we can make in cosmology. So to do that, we need a model of string cosmology, for example, or string gas cosmology model. Now, the way that we can make predictions for cosmology is that we study the early phase, the string gas phase, and then we study the inhomogeneities and anisotropies which are generated in this early phase. We follow their evolution to the present time, and we make predictions for current observations. So let me expand on that a little bit. If you take an astronomy textbook, unfortunately, these astronomy textbooks in their cosmology chapter will say that the universe began with a phase of inflation. And they will say that inflation has been confirmed. So what does one do in inflation? One studies this early phase, hypothetical phase of inflation. One studies how inhomogeneities are generated, and one makes predictions for observations. So what we are doing in string cosmology is exactly the same thing, which standard cosmology, the current paradigm, makes. So we make predictions for the distribution of galaxies, and we make predictions for anisotropies in the microwave background, so the temperature maps of the microwave background. And okay, we can make in our string cosmology model, and I think in any model that correctly comes from string theory, we will be able to make the specific prediction that the gravitational waves produced from the early universe will be different from the gravitational waves produced by inflation. Now, if I want to make a technical term, I use a technical term, a blue tilt of the spectrum of gravitational waves, which essentially means that on small length scales, the gravitational waves will have a little bit larger amplitude than on large scales. Whereas inflation predicts exactly the opposite. Now, we can make even more predictions. We can actually predict the amount by which you have more structure on small scales than on large scales. Okay, so now experiments that probe the cosmic microwave background, the cosmic microwave background polarization, they have the potential to detect gravitational waves and to measure the spectrum of gravitational waves and to determine whether the spectrum has a blue tilt or a red tilt. And let's say 10 years ago, maybe a little bit less than 10 years ago, there was a lot of excitement by a particular experiment, the BICEP experiment, which had claimed to have detected the polarization of the cosmic microwave background. And if those results had been true, they were not true because they were actually dust. Then what was measured by that experiment was actually a blue tilt and not a red tilt. So to come back to your question, yes, I think string theory can make and will make predictions for cosmological observations. But again, the warning is, let's assume that a year from now, high precision cosmic microwave background experiments find gravitational waves and find a blue tilt. Well, this will be a success for string theory, but it will not confirm string theory. So again, it's always a warning. This is obviously, I will celebrate, but with the knowledge that it's just, it is a successful connection between string theory and observations, but it doesn't absolutely confirm string theory.
The idea of string as cosmology differs substantially from the widely accepted idea of the inflation. Could you please contrast these two and help us understand?
Let me explain a little bit about inflation. So in the inflationary scenario, what you do is you take our current universe, you go back, you trace it back using the usual equations of Big Bang cosmology until the temperature becomes extremely high, quite close to the scale where you know that quantum gravity effects will have to be included. And then you hypothesize that at these high densities, there was a phase in which the energy density was constant and space expanded exponentially. So that's the idea of inflation. If we trace the current size of the observed universe back to the end of inflation, it maybe had a size of a couple of millimeters, maybe a centimeter, something of that order of magnitude. But in the inflationary paradigm, this patch comes from a patch which was many orders of magnitude smaller. Again, now I'm going to use mathematical jargon. It's e to the 50 times smaller. Okay, now in string cosmology, we do this similar thing. We take our current patch of the universe, our current observable universe, we take it back to temperatures close to the temperatures where inflation is supposed to happen. This happens to be the string scale. And now in string cosmology, what happens is that the universe doesn't come, it's still, so the patch of the universe that we see today, it again has a size of between a millimeter and a centimeter at this high temperature, at the string temperature. But that's the maximal temperature, and the universe doesn't arise from a much, much smaller patch. So now you see that this exponential increase of a patch of the universe is very problematic. And in string cosmology, we don't have these problems. And these problems, they run under the name Trans-Planckian censorship hypothesis. And they're basic, in my opinion, and what I'm saying now is not accepted by the community, but I actually believe that the inflationary scenario, the way that we understand it today, the way we treat it today, is in conflict with the basic laws that underlie the physics that is being used. It is in violation of the second law of thermodynamics, and it is also non-unitary. So here I'm using, again, a technical term. So the models are very different. In the inflationary scenario, it is assumed that everything that we observe today comes from quantum vacuum fluctuations. And the idea there is the universe undergoes this phase where space expands exponentially. Anything that's there at the beginning of this phase just is diluted exponentially, and you're left with a quantum vacuum. So in the inflationary scenario, it makes sense to assume that everything that we see today comes from quantum fluctuations. Now, in string gas cosmology, or in other models of cosmology that come from string theory that improve on string gas cosmology, there the universe starts with a thermal bath of strings. And in any thermal bath, you have thermal fluctuations. So in our string cosmology model, all the fluctuations come from thermal fluctuations as opposed to quantum vacuum fluctuations.
What is the future direction of your work, and what is the idea of matrix theory?
So string theory is a theory in development. So let me make an analogy with point particle theories. So we've known for centuries how point particles interact classically. And for about 100 years, maybe a little bit less, we also know how quantum effects affect the interaction of point particles. We know how point particles scatter quantum mechanically. And then in the 1940s, 1950s, people then developed a picture that a consistent quantum picture of how point particles interact. So, and in this consistent picture of how point particles interact, particles are replaced by fields. So let me make an analogy with light. So we all know from everyday experience that light is a field. It is an electric field, a magnetic field, which lives everywhere in space. But there are particles associated with light, and these are the so-called photons. And the particles of light can be viewed as localized excitation of this field, which lives everywhere in space, this electromagnetic field. So this is quantum field theory. So we've developed that. This is a very complicated theory. And the key point is that the building blocks of quantum field theory are different than point particles. So now in string theory, we know how strings interact classically. We know how strings interact quantum mechanically, but we don't know the underlying theory that corresponds in point particle language to quantum field theory. So this is missing. And so I'm interested in exploring attempts to develop a consistent theory, string theory, non-perturbative, and then to apply that to cosmology. And hopefully this will put our toy model of string cosmology, which Prof and I developed, onto a firmer ground. So this is one direction. And then another direction is to basically make more predictions for observations that come from our string cosmology model. So I think these are two main directions, which I'm really excited about. And in the longer term, there's the mystery of dark energy, which you brought up in an early question. What is causing the acceleration of the universe? The only thing we know right now about dark energy is that it is there and that we know nothing about it. And I would like to make a link between string theory and dark energy. And I actually have the wild hope that a connection can be made. So lots of exciting things to work on.
What do you think is the next promising direction that the use of string theory in cosmology could lead us in?
So I would like to see a more consistent model for the very early universe. This is the basis of making predictions, you see. So I think cosmologists need to talk to string theorists. And unfortunately, what has happened in the last 20 years is that there's been a big gap that's opened up between the two fields. Cosmologists are happy most cosmologists are happy analyzing data in the context of their existing toy model, whereas for some reason string theorists have moved away from cosmology. So that's the first thing that needs to be done. And secondly, I think one needs to tackle the mystery of dark energy.
Thank you very much for this wonderful session. Lastly, what piece of advice would you like to give to a young audience?
This is a very good question. So let me give some give a personal background. So I actually ended up in the field of cosmology completely by accident. And I was a graduate student at Harvard, and a friend of mine, a fellow graduate student, one May, came up to me and to a couple of others and said, why don't we do something completely different over the summer? Why don't we learn something, study something which is new, and we do that independent of any person with a PhD. And this person was Jenny Trashen. She'd found a preprint, which sounded interesting, which was the preprint of Alan Guth on inflation. So at that point, cosmology was a new field, completely new field. And so this was very exciting, and we could do new things. So my advice to a student is to always keep your mind open to new areas. And another advice is you should work on something which you should work in an area where there are either conceptual mysteries or else lots of data that needs an explanation. And if you're very lucky, it will be both. So you see, right now in cosmology, in my opinion, you have both. You have lots of data, new telescopes are coming online, and you also have the mysteries of dark energy, of the origin of the universe. So right now, it seems to me that cosmology still fits the bill. But you see, now I may actually be old-fashioned. So a young student should consider what I just said at the very end critically, and should look at the kind of data that we will get, and ask the question, is that really going to be fundamentally new and interesting? And should look at the fundamental questions and say, maybe these are not fundamental enough. But so my advice to a student is you should look at areas where there's unexplained data and where there are fundamental mysteries.